Hey guys, this is Mr. Sell. You guys need to have that blue sheet and get started on this stuff. This is the bell work, and have a good Halloween. Of course, at the end of the lesson, you guys are going to want to pick up a computer and get started on the assignment. But take a minute and get started on this first. All right, so hopefully you guys got those 6 done. Here are the answers. And yeah, you should be using bar notation where the decimals repeat, specifically like number 6, where only the 7 repeats. That's the only number you need the bar over instead of, you do not need it over the 1 there. All right, there's our objective for the day. I can solve equations with 1 or 2 principles of equality. Just take a minute and copy that down. All right, hopefully you guys got that down. So this is on your worksheet right here. What is a solution? A solution to an equation is a value for a variable that makes the equation true. So when we say true, because it is an equation now, and we talked about this a little bit last time, an equation is when you have 2 math expressions that are now equal. So you got an equal sign in between 2 different expressions. Now you're going to see it like this. It's going to say solve for x. Now, or solve even. If you see these 2 statements, what it's really asking is what value of x makes the equation a true statement. You'd be better off in your brains asking what value of x makes the equation a true statement, because it's going to force you to think about if it does make it true or not, which hopefully will help us to remember to do the final step on all of these, which is just to check to make sure that it gives you finally a true statement. So here's an equation. What is the solution to the following equation? All right. Now this one is actually pretty direct. It actually gave us the answer right there. But what is the solution to the following equation? Again, we can rephrase that question and ask ourselves, what value of x would make this a true statement? Well, if you replace that x with 10, then the equation would show 10 equals 10, and that right there is true. Now, again, that was direct because they told us in the beginning x equals 10. So replace x with 10, right? Not too bad, but of course we're going to be expanding on these, this type of expression as we continue. So keep that in mind. This is kind of what you'd be looking at the end of solving these types of problems, is something like this. So let's expand then, right? So now it's not just x equals 10. It says x plus 2 equals 10. What value of x would make this a true statement? And I know, well, several of you could do this in your head. If you can, that's fine. But just think, what number plus 2 is 10? And then hopefully you'd realize that if you said x was 8, right? If you replace this x with 8, then you get 8 plus 2, which is 10. And 10 equals 10. Yeah, that's a true statement. So since this is true, now we know that x equals 8. Now, naturally, with mathematics, we're going to come up with some principles that we can apply to any type of problem like this, which will then help us to solve this in a more mathematical, algebraic method. All right, so that last one had addition. Next is subtraction, right? So what number subtract 3 equals 10? And again, this, hopefully some of you guys got this just without having to show any work. You would know if you replaced x with 13, then you would get 13 minus 3, which is 10. And that also would be a true statement, right? We'll show the work on that. 13 minus 3. And, you know, right now we'd say, well, we're not really sure if it's true, but 13 minus 3 is 10, which does equal 10. That's true. So again, since we see this creates a true statement, then I would feel more comfortable boxing in my answer like this. So in this case, in this equation, x minus 3 equals 10, x equals 13 is the solution. It makes it a true statement. So that's addition, subtraction. Now multiplication, and again, there is multiplication between the 2 and x. We don't show the multiplication anymore because we're lazy math people. So 2 times x equals 10. What times 2 equals 10 would make that a true statement? And again, this should be fairly easy. If I said, if I replace the x with 5, then I should get a true statement, right? Because 2 times 5, does that equal 10? Well, let's find out. 2 times 5 is 10. So that equals 10. That's true. And again, now that I've confirmed that it is true, I see x equals 5 is true, or makes it a true statement. So therefore, it is the solution. It makes it true. So that's addition, subtraction, multiplication. So obviously the next operation will be division. Something divided by 4 equals 10. This one may take a little bit more thought because of its a division on this one. And just from time to time, you guys, sometimes we get students that are like, well, 10 divided by 4 is 2.5. But that's not what this is asking. And you could even check, just like we have been doing. 2.5 divided by 4 definitely does not give you 10. So it's definitely not 2.5, okay? We kind of went in the opposite direction on that one. And some of you guys are thinking in your brains, which is really good if you do. You'd say, well, then you do 4 times 10, right? So x equals 40. And yes, that's correct. If you said x is 40, then you'd be correct because, and we'll show it, you'd have 40 divided by 4. Does this equal 10? Question mark. Well, 40 divided by 4 is 10, which, yeah, that does equal 10. That's true. And since we've confirmed that it is true, then we can box that in. Now, I did show the 4 times 10. That is one of the principles that we're going to be looking at on this. They're called principles of equality, which we're going to need to know in order to proceed through this unit. If we misunderstand any of these principles of equality, then the rest of this unit could be really, really tough. All right, so as of right now, we're looking at equations that only require one of these principles of equality. And we are manipulating these equations so that we just end up with x equals something, just like we've seen in those last 4 problems. But addition, you can see, this is all abstract, you guys, which I don't really care for because sometimes it's not so understandable. But this is saying a equals b, right? Then, if this is true, then you can add the same thing to both sides, and it still remains equal, okay? Or you could say, if they're equal, then you could subtract the same thing from both sides. Or you can multiply the same thing on both sides. Or you can divide the same thing on both sides. Generally speaking, most teachers will say, if you do something to one side, you got to do the same thing to the other side, okay? And that's kind of the phraseology that I'm going to be using. Whatever you do to one side of the equal sign, you got to do to the other side. Okay, and that maintains equality. And we can check this. And again, we're only looking at this with one of these principles of equality. So if I said something like 10, we already used 10. Let's not use 10. Let's use, I don't know, 3. All right? I say 3 equals 3. And you could confirm that 3 does equal 3, and you'd feel pretty good about it. It's like, well, yeah, I already knew that. Well, as it turns out, if I said, well, 3 plus 1, see how I added that 1 in purple? If I keep it like this, if I only do it to the left side here, it gives us a false statement now, right? You end up with 4 equals 3. So if I do it to the other side, though, then it remains true. Okay? Because now 1 plus 3 equals 4, and 3 plus 1 is 4. Okay? Let's look at this a little differently. I'm just going to need more space on this one. Okay, we'll still use 3, though. Let me try that again. So we got 3. 3 equals 3. That's a true statement. We feel good. Okay? But if I said, well, 3 minus 2, right here, right? That'd be 1. But if I keep that red 3 on the right the same, then it's going to give us a false statement. So I also have to subtract 2 on that side as well. Okay? So this is just showing you whatever you do to one side, you got to do to the other side. And if we continue this with other operations like multiplication, still true. In fact, if you were to divide this, it would give you the same decimal, 1.5 there as well. Okay? Now, we didn't start with that divide by 2 or multiply by 2 or subtract 2. We started with 3 equals 3, right? Well, sometimes it doesn't always look like 3 equals 3. Sometimes you may end up with a situation like we've seen already, something like x plus 2 equals 10, right? And then you'd say, whatever I do to one side, I got to do to the other side. It's just there's purposes for these, okay? These principles of equality. And up here I use the word manipulation because it's about you taking control of the math and not the other way around, because math has been known to destroy people's lives. All right? So, when you look at these, particularly addition and subtraction, that's when you're looking to, I don't know, I'm going to say make or manipulate. You're going to make zeros. Okay, addition and subtraction is how you make zeros. And I have talked about how zeros is one of those numbers that math people really geek out about. I mean, they're already nerds, you know what I'm saying? But it's like, dude, if you start talking about zero, they'll talk about zero all day long until, start banging your head against the wall. So, multiplication and division, this is when you want to make ones. Now, we have talked about this just a tiny bit, zeros and ones, but we're going to go into these in more details. These can be phantom values based on the operation that's being performed. Such as, if I said, and let's just look at the 3 there at the bottom, right? If I said 3 plus 0 equals 3 plus 0, you'd say, yeah, you didn't change the value, right? Well, what if I didn't show the plus 0 right there? See that right there? Did I change it still? No. I just didn't want to show the plus 0. Why? Well, maybe you feel like it's ugly. Or, I don't know. I feel like we do that to people that are zeros, right? It's like, you know what, we're just going to ignore you and leave you alone, all right? Not that we should, but it happens. So whether you want to show it or not is up to you. Generally speaking, though, we don't show it, just like we are not showing this plus 0 right there. It's there. It's watching. It's looking. Kind of creepy. But we just don't want to show it, okay? So it's an invisible, or I call these phantom zeros. And again, this is with addition, right? Addition, you could say subtraction if you like. Well, let's change the operation. Let's go back. And again, for multiplication and division, you'd say, well, that's how you make ones. Okay. Right? Because if I said 3 times 1, and over here I said 3 times 1, it's the same thing. But what is 3 times 1? It's just 3, right? So again, I make that a phantom 1. It goes away. It's still there. It just disappeared. So yeah, that's the creepy part of it. It's a good time of year for that, with Halloween being on Saturday. But yeah, those phantom 1s, That'd be nice to come to school as a Phantom 1, you know, or a Phantom 0. I guess I have to build for a Phantom 0, you know, because I'm fat, but that's a whole different story. So, yeah, in the equations, you'll see a number and you're going to be like, I don't want you to be this number, I want you to be a 0. Or I want you to be a 1, and then you're going to use those specific principles of equality to make specific values become zeros and ones. And again, we'll talk about that. Just remember, and that's part of the principles of equality. Whatever you do to one side, you got to do it to the other side as well. It will be crucial for you guys to understand that. So on this problem, 18 equals 20 plus v, and yes, some of you guys are like, I already know that answer in my head. Alright, that's great. But I am going to show you guys this using the principles of equality. Because, well, that's kind of our objective. They've got to be able to learn them and use the principles of equality. So some of you guys are like, I already know v equals negative 2. That's great. Good for you. But let's show it with some work, okay? So that 20 plus v, now remember, and it is good that you guys know that what we really want is just v equals, right? Now, if I said, what's the coefficient of v right now in the top equation, 18 equals 20 plus v, it would be pretty crucial for you guys to know that the coefficient of v right now is a phantom 1. Okay, now again, I'm going to show it as a phantom 1. Now, the v that we get down here, because it's just v equals, is it being added or subtracted to anything? You could say, yeah, you could, if you wanted to. You could say, well, and I am showing this specifically like this on purpose. You could say that it's 0 plus v if you'd like. But do we usually show 0 plus some value? No, we don't. We usually make it a phantom 0 right there. Okay. Now, I am going to show it, though, because there is a point I'm trying to make on this. See that 20? I got 20 plus v, not 0 plus v. So how do I make a 20 a 0? Well, making zeros, we know that's either the principle of equality of addition or subtraction. And if I took a positive 20, because this is positive, I'd have to subtract 20 to make it 0. Now, that was kind of arbitrary right there, right? I said 20 minus 20, that gives us that 0 right there, right? But this is where the principle of equality comes into play. I just subtracted 20 on that right side of the equal sign. Just make sure you do it to the other side. And then we get negative 2 right there, right? So simplifying this and making that a phantom 0, we get v equals negative 2. So you could check, you could say 20, let's show the full thing. 18 equals 20 plus v. This is the equation they gave us. But now, right now, we think that v equals a negative 2. All right, so we'll check for truthfulness on this. And 20 plus negative 2 is 18. Yeah, that's a true statement. And since it is true, now I would feel a lot more confident about my answer down here. Negative 2 equals v. Now, I'm going to reiterate this just because it is right now. We're looking at using one principle of equality. Yeah, maybe I spent more time on that than you needed, but it's crucial that you understand these principles of equality. So on this one, negative 27 equals b minus 40. And it says solve, so we want to know what value of b makes this a true statement. And what we would really like is just b equals something, right? So that means I don't want that minus 40. I'd rather have it be a plus 0. And the coefficient of b is a 1, which will be pretty important later. So I need a 0 out that negative 40 so that it becomes a phantom 0. Well, just add 40 right there. Okay. Now, going back to, I think it was the second lesson, maybe asking, well, why is it considered negative 40? Because it takes the operation to its left as its sign. So it's really considered a negative 40 right there. Okay. Well, what did that do? Negative 40 plus 40? Yeah, that's 0 right there, just like we want. Negative 27 plus 40, that's going to be 13 right there. And then the b we're just going to drop, because we did not operate on the b. Okay. So I end up with 13 equals b, and we could just check. You could just use a calculator on that. So I type in 13 minus 40, and when I push enter, I should get negative 27, which I do. So that confirms that 13 does equal b. And you bring up a good point as well. What we've written right here, 13 equals b, it's the same as saying b equals 13. So whether the b is on the left side or the right side of the equal sign doesn't matter. It still means exactly the same thing. For this problem, it is important to know what operation is between the negative 6 and x, and of course it is multiplication, which is good. Now remember, just like we've seen on those last couple problems, is we really just want it to be x equals something, not negative 6 times x. And going back, and I said this was important because it is, if we look at this x down here, what is its coefficient? It's a 1, right? You could already say it's being added to 0 right there. That's a phantom 0. That's fine, no problem, okay? But that negative 6, that's no good. What I would really like is the coefficient to be a 1. And then we say, well, how do you make a negative 6 become a 1? Well, remember, to make 1s, we either need the multiplication or division property of, principle of equality. So in this case, you'd say negative 6, if I just took negative 6 and divided it by itself, then I get 1. And yes, you can make it a phantom 1 if you like. But just remember, since I divided the left side here by negative 6, you got to do it to the other side as well. So 36 divided by negative 6 also is negative 6. And you could check, right? Negative 6 times negative 6 in the calculator. And we push equals, you do get 36. So that's a true statement. And just box it in and call it a day. Well, not a day because we got more problems. Alright, so here's another one, and again, we need to identify the operation between the w and the negative 9. That's division. So we don't want anything divided by the w, we just want it to end up being w equals something. That would be really nice. But right now, it's that divide by negative 9 is stopping us from seeing just this regular w. Well, this is where we would say, or we would start using what we call inverse operations, and right here with the division sign, you'd say, well, what is the inverse of division? Something that undoes division, which is actually multiplication. Okay, so I'm going to multiply this by negative 9, and really this ends up being, we would switch the two and say it's negative 9 divided by negative 9. The reason that is because it becomes a phantom 1 right there. I'm showing it so it's not a phantom 1 anymore, but it is a phantom 1. It's going to be a phantom 1, so we don't like to see that garbage. Just remember, yeah, if you do it to one side, you got to do the other side. Negative 4 times negative 9er, boom, 36. So let's just check, right? 36 divided by negative 9, I put that in the calculator, I push equals, bam, negative 4. And you even have the fraction button if you'd rather see it as a fraction, right? The N over D button. So I assume we're talking about this 9 on the left, the negative 9 right there. That becomes what we would consider fraction multiplication. It's really negative 9 over 1. So, right, you'd say fraction multiplication, you'd have negative 9w over 1 times negative 9 is negative 9. And that's why these cancel out as a phantom 1. Now again, we have talked about equations versus expressions. Equations just have equal signs, and it's usually between two expressions, of course. And yes, x is by itself its own expression, and same with an individual number, but sometimes they're bigger than that. Now, what we just did is just solving equations with just one step, right? It took one principle of equality, we solved it. Now we're going to look at using two principles of equality to solve these ones. So the principles of equality have not changed, but the look of these has changed, okay? Now remember, the principles of equality, we got addition and subtraction, that's to make zeros. And we got division and multiplication, which is usually to make ones. And we know in the end, we just want it to be x equals something in this case, right? Now, the first thing you should always do is isolate your x's, okay? Well, actually, technically speaking, you'd say, is there any distribution? Is there any like terms to combine? That was our second lesson from last time. But just with two-steppers, you'd say, I want to isolate my x's. What that means is I just want it to be 2x equals something. Which means, you see how that gets rid of that plus 4 right there? It zeroes it out, so you'd say, I'll just subtract 4 from both sides. right there. So drop your 2x. The 4 minus 4. That zeroes out. We made a 0 right there. And then 10 minus 4 is 6. All right, now that's one step. The second step here is to make the coefficient of x a 1, right? Because then it would just give us x equals something. And again, whether you show the phantom 1 there or not is really up to you. So yeah, I would say divide both sides by 2 to make that 1. Remember that 2 divided by 2 is going to make it a 1. And 6 divided by 2 is 3. So as of right now, we think x is 3. But let's just check on the calculator. So that's 2 times x. So I'd say 2 times 3 now instead of x because we think x is 3. And then I put plus 4, and then I push enter, and my calculator tells me it is 10. So now I know that x equals 3 is the actual solution here. All right, let's get started on this one. So once again, let's isolate our x's. Now there's negative 3 of those x's, which is fine. It doesn't matter if it's negative coefficient right there. And we just want it to equal something, which means that plus 1, you're going to have to zero that out. Okay, there we go. So that plus 1, how do you make it a 0? Yeah, just subtract 1 from both sides. Now you guys see this upside down t right here. That's what some students have called in the past. You don't have to show it like that. I like to do it just so I can see if I do it to one side, I have to do it the other side of that line. Which really, this one right here, that represents the equal sign right there. And it even brings it down right there, right? So we dropped the negative 3x right there. Negative 14 minus 1 is negative 15. And then the 1 minus 1, that did exactly what we wanted it to do to become a 0. Let's say that you did. You said, well, I got to do it to all the terms right there, right? See on the right side of the equal sign how I subtracted 1, but then another 1? That would be like subtracting 2 total value from that side.
So you have to subtract 2 from 14?
That's right. Now, the problem with that, though, is it becomes, well, even showing that negative 1 right there like this, the negative 3x minus 1, they're not even like terms 2 combined, so they're not even combinable at that point. So the next thing we want is a coefficient of x that is 1, right? We want that 1 coefficient. But right now it's a negative 3, dang it. So let's make it a 1. Let's force it against its will to do our bidding by dividing it by negative 3. Just divide it by itself. Anything divided by itself is 1. Now, maybe in the future your teachers will be like, see how I crossed that out? I didn't just cross it out, you guys. That's a 1. But, you know, we're going to make it a phantom 1 in the problem. Whoops. Let's see. There we go. And negative 15 divided by negative 3 is 5. So let's check. Let's check real quick. Negative 3 times 5, because it was times x, and then plus 1 equals, bam, negative 14. So it is a true statement. And now I can box that in with great confidence. For a problem like this, if we just know what the coefficient of g is, this one helps us. It's not even a two-stepper. But you guys are going to see problems like this, which is important for us to be able to know how to do. Some of you guys would say, oh, there is no coefficient of g, but there is. It's a phantom. It's not even a 1. It's a negative 1 right there. But we don't want a negative coefficient. We would like a positive 1 coefficient. So how do I make that negative 1 a positive 1? Again, you're making a 1, so just divide it by itself. That's how you make anything 1. So that becomes a 1, 1g, and yeah, we'll make it a phantom g right there. And then we got 18 divided by negative 1. Because whatever we did to that left side, we had to do to the right side. So then it becomes a negative 18.
We were right.
And it is true that some of you guys would just be like, can't I just move the negative here to the 18? You could. You could. Just be careful because in the future, like if it was negative g equals negative 18, then you'd have a negative 18, which is just positive. Okay. But for now, negative of negative 18 is that positive 18. That's correct. All right, quick review on fractions. What is a fraction? Really the fraction line. What operation does it represent? It's division. Yeah, and we've done this one, right? So yeah, you guys remember on this problem we said it was w divided by 9. And technically that makes the coefficient of 1 over negative 9. That's not important right now though. It will be though. So we said, you know what, we're going to do the opposite or the inverse of division by multiplying this side by -9, but if I do it to one side, I do have to do it to the other side as well. That made a phantom 1 there, and we got W equals 36. Okay, -4 times -9 is 36. And we've already checked that one, but whenever you see a fraction like this, just multiply both sides by the denominator. That will get rid of the denominator as a phantom 1. Boom. Okay. So on this one, if I can get that fraction by itself, because that divide by 4 is with the x, then we'll be in much better shape. I don't want that -7 is what I'm saying. And when I say I don't want it, it means I'm going to have to zero it out so I don't have to look at that nasty garbage. So how do you make a -7 a 0? Just add 7 there. But if you do it to one side, please do it to the other side so that you maintain equality. Alright? So we're going to take that x over 4, just drop it right here. -7 plus 7, that zeroes out just like we wanted. And -1 plus 7, that's going to give us a 6 right there. So we've isolated that x, or a fourth of an x anyways. But we don't want a fourth of an x. We want a whole x, a 1x. So just give yourself 4 of them. Multiply that by 4. But if you do it to one side, you got to do it to the other side. That becomes a phantom 1. And so we get x equals 6 times 4, which is, 24. Which becomes important when we check this, right? Because right now I got a fraction, so I got my fraction button, 24 over 4 minus 7. And when I push equals, what should I get? -1, which I do. And since I do, that's true. But yeah, we don't want to interpret that -7, which makes the term itself negative, as a multiplication of -7. Which is why the minus becomes the operation, but also the sign. If it was just x over 4 times -7, we want that -7 in parentheses, or we would actually have to show the multiplication sign. Alright, so once again, even though it's got a fraction, no problem. We just don't want that +9 right there, so subtract it from itself to make it a 0. So 24 minus 9er, boom, 15. Is going to equal, we'll just drop this x over 5 right there. And sure enough, 9 minus 9, that did zero out. So I got a fifth of an x is 15, but I don't want a fifth of an x. I want a full x, so just take 5 of those. But once again, if you do it to one side, you should do it to the other side. That becomes a phantom 1, and x now equals 75. Now, like you guys said, though, I mean, something divided by 5 plus 9 equals 24. Like, if you can do that in your head, more power to you, man. Like, maybe it's just because I've been trained so often, or I've done so much of this math that I'm like, yeah, I better subtract 9 from both sides and then multiply by 5, whatever, okay? But I am going to check on the calculator, right? 75 divided by 5 plus old 9er, and when I push equals, I should get 24. I do. Therefore, I know 75. If I replace the x with 75, I get a true statement. Bam. Yeah, so these are two-steppers, right? Because you guys saw we used the subtraction principle of equality and then the multiplication principle of equality. Now, just keep in mind, right? In the future, it's going to be more than 2 steps, more than 2 principles. But not only are we going to have more principles of equality involved, but you're going to see that you're going to need distribution like we did in lesson 2. And also combining like terms, which we did in lesson 2. Okay. Again, we don't see as much factoring. That'll be saved for a later time, probably next year for you guys. But don't worry about the factoring thing. I mean, we may see it on the test, so we'll review it, but it doesn't really show up in terms of solving equations like this. Okay. So hopefully you guys feel pretty good about the objective. I can solve equations with 1 or 2 principles of equality. Again, we'll expand on this by using distribution and combining like terms, but for now, we just got to be able to use those 2 principles of equality, okay?